Hi everyone, welcome to Math 261. This is Scott. Let's get started. Math 261 is called linear algebra, and the reason why it's called that is that it's mostly a matter of dealing with systems of what are called linear equations, and that's what we'll be focusing on right here in this section, section 1.1, the beginning of it all, what it's all for, systems of linear equations. Systems of linear equations. Alright, so here is the setup. So the setup is that we will have a collection of linear equations, and those will be equations in several variables, and those variables will all be shared by all of the equations. So we're going to have a collection of linear equations. Now, what I mean by that is that the equations are going to involve only variables multiplied by coefficients added together. No combinations where you have one variable times another, no variables in denominators, no variables raised to any exponents, anything like that. So a collection of linear equations that all share the same variables. And in particular, we'll call those variables x1, x2, x3 up to xn. So in previous math classes, whenever you've had to deal with equations that involve multiple variables, they've usually been something like x, y, and then z perhaps, and maybe there's a t in there for time, something like that. But in order to make things nice and systematic, what we're going to do is just use the letter x for all of them, and then use little subscripts to distinguish them. Alright, and then the goal in most applications, and in particular in this section, is to focus on the solutions to these equations. So find combinations of values that would simultaneously satisfy all the equations. In the system. And in particular, what we're looking for is the solution set. So this is the set that characterizes all such combinations. Solution set. This is a set that characterizes all solutions to a system of linear equations. Okay, so this is the Holy Grail, this is what we are after, this is what it's all about. So now, let's consider the possibilities for what can happen in our systems of equations as far as their solution sets. So there are three possibilities. Possibility number 1. So it may happen that the system of equations is inconsistent, which would cause there to be no solutions. So the solution set is empty. So there are no solutions. No solutions. In other words, an empty solution set. And one way of writing that is with the classic symbol for an empty set, which is like an O with a cross through it. So this is a Norwegian letter. It comes from the Norwegian mathematician Abel, who was the first one to introduce it. It's like an O with a diagonal slash through it. Or another way of writing it is with an empty set of set braces. So an empty solution set, which you can write this way or often this way. And then another way to describe this is that it is an inconsistent system. Okay, so that's one possibility, is that there are no solutions at all. Now, that's sort of the worst case scenario. The best case scenario is that there is a solution, and in fact, there is only one solution, one unique solution, as we say. So one, and we'll usually describe this as unique. Solution. So what this means is that the system has one particular solution, one combination of values, one for each variable, which ends up then satisfying simultaneously all of the equations. There are no others, and there is no inconsistency. So this is one set of values that satisfy the system. Okay, and then third case would be there might be an infinite number of solutions, which then we will characterize as a solution set or a family, and we will parameterize it using a parameter such as t. So there might also be an infinite family of solutions. And here we can call it a family parameterized by a parameter. So we can usually described usually described via a a parameter. But we'll describe, or we'll deal with that more actually later on. For now, in this section, the first two of these possibilities is going to be our primary scenario. So in this section, we're going to be looking specifically at possibility 1 and possibility 2. We'll deal with possibility 3 in later sections because it's a little bit more complicated to deal with. So let's describe now what it is that we can do in order to find these solution sets. Now, the main tool that we're going to be making use of in this course is what is called row reduction. So let's see how this works. So solving systems. Whenever we say systems in this course, we'll mean systems of linear equations via row reduction. So this will be the main technique that we'll be making use of. We'll be a little bit more flexible with it than say a computer would be, but it's always going to be our main go-to technique. All right, so let's discuss what the overall goal is when we do this and how it works. So the goal: use legitimate mathematical operations to rewrite the equations until the values of the variables are revealed. Revealed. All right, so a couple things here. Legitimate mathematical operations until the values of the variables are revealed. So those are, so got a little bit to unpack there. So first off, the legitimate mathematical operations to rewrite the equations. Let's discuss those. So the setup that we're going to start with in all of these is that we're going to have the equations written such that all of the variables are on one side and the constant terms are all on the other. And furthermore, we're going to order them all consistently as far as the terms that include each variable. So first, the setup is to write all the equations in what's called standard form. Standard form. And by that what we mean is that the terms that contain the variables with their coefficients are on one side and then the constant terms are on the other. And in particular, the variables will be on the left. So variable terms on the left, constant terms on the right, and variables all written in the same order. So for example, so here's the first system that we're going to solve, and it's going to look like this. So we can have three variables, x1, x2, and x3, and our system can look like this. We can have x1 plus 2x2 minus 5x3 is equal to negative 10. And then maybe we have negative x1 plus x2 and then minus x3 is equal to negative 2. And then as our third equation, let's say what we have is 2x1 minus 3x2 plus x3 is equal to negative 1. So here's a system, and what we have done with it is, however it was to begin with, we have rewritten it so that all of the terms that include the variables are on the left side of the equation, and they're all in a consistent order. x1, x2, x3, and then all the constant terms are on the right side of the equation. So this is going to be our home base. This is going to be our first position that we'll be starting from in all cases. Okay, now let's discuss the mathematical operations we can do to the equations once they are written in this form, with the ultimate goal of being able to discern what is x1 equal to, what is x2 equal to, what is x3 equal to. So here are what we will call the row operations. And these will be the row operations that we will use in the course of row reduction. So the row operations that we are allowed to do will be the three following categories. And it turns out that these three operations are enough to solve all solvable systems of equations. If there's no solution, then that's another matter. But if there is a solution, these three operations will be enough to find it. Okay, so here we have the first one, which is multiply both sides of an equation by a non-zero constant. Oops. By a non-zero constant. Now clearly, as you know from all your algebra classes in the past, this is a legitimate operation to do on any equation for any reason. You can always multiply both sides of any equation by the same non-zero constant. The reason why it can't be 0 is then what you get would be 0 equals 0, and although that would be a true statement, it would not be equivalent to the original equation. But if you multiply both sides of an equation by 2, or by 1/2, or by negative 1/3, or something like that, then the resulting equation will have all the same solutions that the original one did. So we call those equivalent equations. So multiply both sides of an equation by a non-zero constant. And we call this operation scaling. Scaling because we're scaling up or down the equation. Alright, we can also interchange the position of any two of these equations. There was no law of nature that said this equation had to be written first, this equation second, and this equation third. It is totally arbitrary what order the equations are written in, so they can be changed willy-nilly without even so much as an apology. So, we can interchange row operations. Multiply both sides, yeah, interchange the position of any two equations. And then the last one. So this one's a little bit awkward to word, but it is a perfectly fine thing. What I can do is I can take one of the equations, I can multiply it by a constant, I can add that to another equation, and I can replace the second equation by this new result. And what that basically is doing is, so you will be most familiar with this if you have solved equations by what is called the method of elimination or the method of addition in, say, Math 95 or Math 65. But anyway, so here's how we'll word it. We can replace one equation by the sum of a constant multiple of another equation and itself. So sum of constant multiple of another equation and itself. So we see what this looks like when we actually try it. It's awkward and confusing to word, but it becomes a sort of second nature. All right, and now the strategy. The strategy behind all of these operations is the following. The goal is elimination of variables. So the goal is to eliminate as many variables as you can from as many of the equations as you can by finding convenient constants to multiply by. So strategy is to eliminate as many variables as we can from as many equations as we can and the way we accomplish this is by finding constants to multiply by, which will cancel the coefficients of the chosen variable. Or chosen variables, let's say. But anyway, enough trying to describe this operation. This is a primarily useful and active thing, so it requires actually just seeing it in action in order to try to understand what's going on. All right, and now one last bit of convenient convention that we'll use. We will rewrite systems of equations in the following way in order to streamline all of the operations that we're going to do. So here's a tool that we'll use. That is to rewrite the system of equations as what is called an augmented coefficient matrix. So the tool that we're going to be using in this is rewrite the system of equations as an augmented coefficient matrix. And the way and what this refers to is, so this is augmented coefficient matrix. What this refers to is an array of values that represent the coefficients in the system. With an augmented column representing the constant terms. So for example, and here, all that stuff may have just been so much gobbledygook and so many complicated words, and you don't know exactly what I mean. But the example will show you what is meant by all this. So the example, if we took the system of equations that we were dealing with before, x1 plus 2x2 minus 5x3 is equal to negative 10, and then negative x1, so this is just the same system as what we had before, plus x2 minus x3 is equal to negative 2, and then 2x1 minus 3x2 plus x3 is equal to negative 1. So then what this will lead to is a matrix, is a matrix that looks like this. So where we just cut out all of the parts that are just there by convention and only put in the parts that change from problem to problem, which would be the coefficients. So what we would put is a coefficient of 1, followed by a coefficient of 2, followed by a coefficient of negative 5 for these, and then we augment it with an extra row for the constant terms over here of negative 10. And then negative 1, 1, negative 1, these are the coefficients of these variables. So again, coefficients of the variables just means the number in front of them, or if no number is written, then it's a 1. And then here goes the constant term, negative 2, and then over here we would put the 2, we would put the negative 3, we would put the 1, and then lastly we would put the negative 1. And we use always square braces on these. And here, when humans do it, it's customary to put either a little gap here or even a little vertical line to separate the two sides of the equals sign. This is often not put in books though, so this is often not present. In books especially. But it's helpful for us humans to put it in there to help us remember which side of the equal sign each of these things is. And to remember that what we're talking about here is not merely the coefficients over here, but the coefficients plus also the constant terms. Okay, now some notation that we can use for the operations that we will be doing would be like so. So we can indicate the row operations we perform as follows. So the notation we can use would be something like this. So let's say what we wanted to do was replace row 2 by the sum of row 1 and row 2. So we could do something like this. So we'd say row 2 in place of old row 2, we could do row 1 plus row 2. So this would mean replace row 2 with row 1 plus row 2. Yeah, put it in here. We could also interchange the order of 2 rows. We could say like row 1 interchange with row 2. So this is interchange row 1 and 2. And then if we want to do some scaling, we could say like row 2 is replaced by say like 1/2 times row 2, just as an example. I'm not necessarily in this case, this is how we would write a scaling factor. So this is scale row 2 by a factor of 1/2. Again, that's not something we would do necessarily in this case, but it's just an operation that would be customary to do. And now in our example, so here, separate the example from what we just said here. So now in our example, what we want to do is we want to take primarily this matrix here. We don't want to rewrite all the x1s, x2s, and x3s at each step of the way because that'll be too time consuming. But what we want to do is we want to take this matrix right here and we want to do row operations on it until what we get is something where each of the variables is a little bit more standalone. And for the first case, let's just and then some more notation to use here. More notation here. So for the we use this. We use a tilde. Represents what is called row equivalence. Which means a new matrix that is achieved by doing one of the legitimate 3 row operations. So row equivalence, so in other words, i.e. a new matrix obtained by legitimate row operations. So right now, what our basic strategy is going to be is to eliminate as many variables as we can, working more or less our way down the line, and then hopefully when we have accomplished our goal, we'll translate our matrix from or we'll translate our matrix back into the equations, and hopefully we'll be able to get somewhere. So here's our basic approach. So eliminate x1 from rows 2 and 3, then eliminate x2 from row 3 Then translate the rows back into equations and do what's called back substitution. So back substitute. Until we get values. For each variable. Alright, so here we go. Back to the example. So the matrix that we had here looks like this to begin with. So it was 1, 2, -5, then -10, then -1, 1, -1, then -2, and then what did we have next? We had 2, 3, sorry, 2, -3, 1, -1. This was the piece that was augmented by the constant terms. These were just the straight up coefficients. And now what we'll do is we'll do the tilde, which means row equivalent, which means what we're about to do is get a new matrix that we produced by doing legitimate row operations to this old one. And now let's think about our goal here. So our goal is to eliminate x1, so get zeros in this column except in the very top, and then after that we'll work on x2 and see where that gets us. But first off, we want to eliminate x1 from row 2, which means we want to figure out what we have to multiply row 1 by in order to add it to this and cancel that. And it's clear that the way that's going to work is what used to be row 2 is just now going to be I guess the new row 2 will be the product of 1 in row 1 plus old row 2. And while we're at it, we're going to do a similar thing here to row 3. Row 3 is going to be obtained by taking row 1 and multiplying it by a -2 and adding that to the old row 3. Now, there's no reason actually why I couldn't have done 2 times row 2 in this step, but here's why psychologically I would prefer not to. The reason I would psychologically prefer not to is that in some sense, if I'm already changing row 2 in this step, I don't want to then use row 2 down here as well. I would prefer not to use any of the rows that I'm currently in the process of changing as I do this. So now the goal here once again was to clear that out from there and that out from there. Now as for the other entries, they are just going to become whatever they're going to become. It's out of our hands really, just have to live with it. So I'm going to take row 1 and add it to row 2, and that'll be the new row 2. Row 1 will be unchanged. So here's row 1, same as it ever was. Now as for new row 2, it's going to be 1 plus -1, which is 0. It's going to be 2 plus 1, which is 3. It's going to be -5 plus -1, which is -6. Then it's going to be -10 plus -2, which is -12. And as for row 3, it's going to be -2 times row 1 plus row 3. So -2 times 1 makes negative 2 plus 2 equals 0. And that was the goal the whole time, was to get a 0 there. Now let's see, negative 2 times 2 makes 4, plus negative 3 makes negative 7. Negative 2 times 5 is equal to positive 10 plus 1 makes 11. And then negative 2 times negative 10 is positive 20 plus negative 1 is positive 19. Okay, so that's where things stand as of now. But we want to continue, and by the way, the way I'll line this up is I put the first original matrix here, and then I put all of the subsequent results down the line here. It's kind of similar to when you're doing operations and you put whatever you started here, and you put equals this, equals this, equals this, equals this, equals this. Same thing, same basic format. Just now we're doing row operations. So now our goal in this is that we want to try to cancel out the x2 from the row 3. Now you'll notice it is not a convenient thing for us at this point to multiply this by something in order to cancel that as yet. However, we can do this in stages, and our next stage might be just to scale this by a convenient factor in order to make this something convenient for canceling that. And in particular, we can't directly cancel it very well right now, but we can scale this down to make a 1, right here, and then that will be fit for canceling the negative 7 by then multiplying it by a 7. So our current goal here is we just want to make row 2 a little bit easier to work with, and you'll notice that row 2's entries are 3, negative 6, negative 12. So they're all factors of 3, so we can just go down by a factor of 3. So row 2 could be canceled, or can be scaled down to make 1/3 of its former self, and the goal here would be to turn that into a 1. You'll see in the next term, or in the next section, that we have a term for, we have a phrase for that, and it's called a pivot. So we're going to turn this into a nice little pivot by scaling it down to make it convenient for operating with. So we have 1, 2, negative 5. We're not changing row 1 at all, really, in this whole operation. In this whole procedure, we're leaving row 1 as it was, and we're just using row 1 first off to cancel here and here, and then after that we basically freeze it. We never touch row 1 again, and we work with row 2 to go down from here to here. And so let's see, multiply everything by 1/3, we'll have a 1, we'll have a negative 2, we'll have a negative 4. And we're not doing anything with this one yet because we're not heroes. We've got to take our time. Oops. See, you can't even rewrite it properly, let alone do something with it. So don't try to be a hero here. We'll get a little bit fancier with our row operations as we get a little bit better at it. But for now, while we're just trying to get our sea legs, we are just going to take it easy. Go nice and slow. Okay. So now that we have it scaled down, we can cancel that 1 down to that negative 7 just fine, and so we shall. And so that means what we're doing is we're going to be replacing row 3 by positive 7 times row 2 plus the old row 3. And what's that going to give us? Well, row 1, as usual, has not changed. So 1, 2, negative 5, negative 10. And then 0, 1, -2, -4. It is not our goal in this step to go around changing row 2 anymore. Row 2 is as good as it's going to get. But now we're going to use that new row 2 to try to cancel that from there. So 7 times 1 plus -7 makes 0. That was the hope the whole time. 7 times -2 makes -14. Plus 11 makes -3. 7 times -4 is -28. Plus 19 is equal to -9. And now what we have here, you'll notice, is what is called a triangular matrix, and it's called that because we've got zeros below the first one, zeros below this one, and that means all of our non-zero entries are contained in this little triangle up here. But more on that as we develop more know-how, more lingo. But the important thing about this for us is that right here we've got a lot of good information going on. In particular, what we can do is we can, if we want, we can scale that down a little bit more, because you can see -3, -9. That's just crying out to be scaled down by a factor of 3 for convenience. And that means what we're doing is we're taking row 3 and we are replacing it by -1/3 row 3. We'd always prefer this to be positive, and we would prefer it to be 1 if it can be in a nice convenient fashion. So there's where things stand. 1, 2, -5, -10, 0, 1, -2, -4, 0, 0, sorry, now it's been scaled down, so it's going to be 1 and 3. And now, what we basically actually have is the end of the road, or at least the end of this road. And so we get off this road and we go onto a different road, we switch it back to equations, and we figure out what x1, x2, and x3 are all about. And in particular, looking right here, so this equation will tell us, well actually let's just write each of these equations in their proper format. So back to equations, we'll have x1 plus 2x2 minus 5x3 equals -10. No great surprise there. That's not so helpful. It's in fact what we just started with. For the next equation, we're going to have only x2. It's going to be 0 times x1, so we don't even bother writing that. Minus 2x3 equals -4. So this is a little different from how we started. A little bit better, but still not exactly anything too exciting. Nothing to write home about. But here, this last one, what we have is 1 times x3. So in other words, just x3 itself is equal to 3. Now that is a very convenient thing. That has told us actually specifically the value of x3. And so then we substitute So we back substitute x3 equals 3 into the second equation here. So x2 minus 2 times 3 is equal to -4. And that means x2 minus 6 equals -4. Which then if we add 6 to both sides, we're going to get x2 is equal to 2. So now we've got answers for what x3 equals and what x2 equals. We know x3 equals 3, x2 equals 2. All that's left is x1, which we again just find by the process of back substitution. We have values now for every variable other than x1. So we put those into the equation. So now we back substitute. x3 equals 3, x2 equals 2. And so we have is x1 plus 2 times 2 minus 5 times 3 is equal to negative 10. And so what's this going to be? X1 plus 4 minus 15. So it's going to be X1 minus 11. So then I would add 11 to both sides, and I get X1 is equal to 1. So then what this means is there is a single unique solution, and that single unique solution is X1, X2, X3 is equal to 1, 2, 3. This will be a common way, by the way, we can express them. Express them as ordered pairs if there's 2 of them, like the coordinates of a point, or if there's 3 of them, then you would do it as an ordered triple, as they say, which then makes a point in 3 dimensions instead of 2 dimensions. But this is where this example took us. We ended up with a single unique solution, and in fact we were able to say categorically what the value of x1 was, what the value of x2 was, and what the value of x3 was. So that was all very nice. Now, what would it have looked like if we were in one of the other 2 possibilities? Because there's no way to tell right now from that what would it have looked like if there was no solution, or if there were infinitely many solutions. So, telltale signs. Telltale signs for other solution scenarios. Okay, so let's start with the no solution. So when you are trying to solve an equation and it turns out not to have a solution, what does that end up looking like? What it ends up looking like is the most basic form of contradiction in all of math, which is to say that something that is not 0 equals 0. So the telltale signs for the solution scenario where there's no solution is you get a row of 0 coefficients but with a non-zero augmented constant term. Now, this may not be the way it looks originally, but when you do the row operation, similar to what we did before, then it ends up looking like that. So as an example, we might have something along these lines. So let's say that as an example, we had a matrix that looked like this. 1, 2, 3, and 4, with the 4 being augmented. 1, negative 3, negative 5, and 6, with the 6 being augmented. And the 2, negative 1, negative 2, 3, with the 3 being augmented. And those are all 3 the augmented terms, or the augmented entries that represent the constant terms. Now, if we were to go about trying to solve this by the typical row operations that we've done, it'd be very similar actually to the ones that we did in the previous example. We would want to clear out from the first column, the column that represents x1, the entries other than the first row. So that means what we'll do is we'll take row 2 and we will replace it by negative row 1 plus the old-fashioned row 2. And similarly, row 3 is getting replaced by negative 2 times row 1 plus old row 3. So what's that going to look like? Well, negative row 1 plus row 2. So first off, row 1 is not changed at all. It's not typically our goal to go around changing row 1. The main thing that we might do in our first step, as far as row 1, is interchange things to get a 1 up in the upper left corner. Otherwise, we are not really going to make that many changes to row 1 unless it is not in a currently useful form. Okay, so we got 1, 2, 3, 4 still. Now we're adding row 1 times negative 1 to row 2. That's going to be 0. Negative 2 plus negative 3 is negative 5. Negative 3 plus negative 5 is negative 8. Negative 4 plus 6 is 2. And there's that. Now, negative 2 times 1 plus 2 is 0. Negative 2 times 2 is negative 4, plus negative 1 is negative 5. And then negative 2 times 3 is negative 6, plus negative 2 is negative 8. And then negative 2 times 4 is 8, plus 3, there is negative 8 plus 3 is equal to negative 5. Okay. Now, you may notice something funny about these last two terms here. They are quite suspiciously similar. But let's pretend like we didn't notice anything. Let's just keep on chugging and not worry about it. Just the next goal here is we'd want to try to do what we can to cancel x2 from row 3. And so what we're going to do is we're going to we notice these are the same number, so if we just multiply by its opposite, that should take care of that just fine. So row 3, this is row equivalent to 2. The result of taking row 3 and replacing it by negative row 2 plus row 3. So that should clear up the x3, or x2 I mean, from row 3 just fine. So here we go. 1, 2, 3, and 4. 0, negative 5, negative 8, 2. And now we're just taking the opposite of these and adding them to row 3. So negative 5 becomes positive 5, add to negative 5 to make 0. Negative 8 becomes positive 8, add to negative 8, becomes 0. Negative 2 plus negative 5 is equal to negative 7. And here, you'll notice something funny about that last little row. As written here, what we've got is 0 times x1 plus 0 times x2 plus 0 times x3 equals negative 7. So in other words, 0, 0, 0, so 0 equals negative 7, which is a contradiction. There is no way 0 equals negative 7. And that is a contradiction, meaning that the system is inconsistent. Inconsistent system, no solution. Or if you are required to give a solution set, then what that means is that the solution set is the empty set, or you can also write it using set braces with nothing in them. So that's a sign of what it looks like when what you have is an inconsistent system. Now, as for what it looks like when what you have is a system that has infinitely many solutions, again, that's not something we're going to focus on so much in this section because it'll be an important matter for us in a lot of other sections and it's a bit complicated. So we'll need a little bit more time to let that topic breathe a bit. But let's just give a little indication of the telltale sign to look for. So infinitely many solutions. What this basically amounts to is you end up with what amounts to more variables than equations. More variables than non-zero equations. And what this means is that you're not able to fully back substitute your way all the way up the ladder. You end up with you can't get 5 pieces of information four out of 4 pieces of information. So you end up not being able to back substitute your way completely. So you can't back substitute enough times. For all variables. So that's what it looks like. So we'll cover this more in later sections. But for now, that is basically that for section 1.1, your first installment of Applied Linear Algebra 1 here at PCC. So, I will see you next time. Until then, bye.